These are 1-4 notes on composite functions. The notes we covered previously in the work we've done most recently was simply on how to evaluate a composite function. What we're going to look at today is how to evaluate, we're going to look at the meaning of a composite function and how to evaluate it not only algebraically, which is what you've already done, but also graphically and numerically, and then we're going to make some applications. So let's start with the idea of a composite function with this example. Okay, we are told that the radius of a circular opening increases at a rate of 8 millimeters per second. So we could find the radius of this circle at any time, right, as long as we knew that time. And we could say that radius is a function of time and could be found by multiplying that time in seconds by 8. So r of t is 8t. So could we find the radius of the opening after 2 seconds? Well, plugging 2 in for t, 8 times 2 is 16, and that radius would be 16 millimeters. After 5 seconds, again, if we replace the time in our equation with 5, 8 times 5 is 40, and the radius of the opening would be 40 millimeters. I feel very confident that you could have done that without my help. Now here's another thing we know about a circle. We know that the area of a circle can be found by using the formula area equals pi r squared. So we've got two things that can vary. We've got the area of the circle, and it varies as the radius of the circle varies. So we can say that a of r is equal to pi r squared. So could we find the area of the circle after 5 seconds? Well, here's the flow of our process. We start with the time, 5 seconds. From there, we would need to find the radius, and we know how to do that when we have a time. And then with the radius, we can find our area. So let's look at this flow chart. We're going to start with our input for the radius function. So we have an input in the radius function, and that is, this should be 5 seconds. We're going to take that input into the radius function, and we're going to put it in for time. And the radius is 8 times 5, which is 40, and this should be millimeters. So 40 is the output from the radius function. Now we're going to take the output from the radius function and we're going to put it into the area function. Okay, so our output from radius becomes the input for area. We plug 40 in for r and square 40, multiply that by the approximation for pi, and we get, let's see, 40 squared is 1600 pi millimeters squared, or 5,207, right? That is our output from the area function. Okay. So you could have done that again, probably without my help, right? But the main thing I want you to capture here is that what we've done is we've taken the output of one function, in this case r of t, and we've used that radius, that output, as the input of another function, a of r. So we could say that area is a function of radius, where radius is a function of time. And making our substitutions, because we know that r of t is equal to 8 times t, we could say that area, right, is a function of 8 times t. Excuse me. And I know that area is pi times its input, which in this case is 8t squared. Using order of operations, we can simplify that, right? We can take this exponent t and distribute it to the 8 in t, and we get our pi times 8 squared, which is 64, times t squared, right? Or we get 64 pi t squared. This is a function for area using t as our variable. So here's the main point that I want you to get from this. Okay. A composite function happens when the output of one function is used as the input for another function. So let's use that idea from a graphical perspective. Okay, so this is how to find composite functions from graphs. We want to find f of g of 30. When we simplify, right, and we have nested parentheses, we've learned in the past that we work from the inside, right, to the outside. So when I evaluate this function, I'm going to start with the inner part of that function. I want to find g of 30. Well, here is my graph of g. So I can find g of 30 by starting with 30. Here's 30 as my input for g, right? Taking a vertical line to my graph, and from that point on my graph, taking a horizontal line to the g-axis, and I would estimate that's about 2.5. So when I find f of g of 30, right, I get f of what I found for g of 30, which was about 2.5. So now I need to evaluate f of 2.5. So I'm going to go up here to the f function, and the input for f is 2.5, so I'm going to go to where 2.5 would be on the x-axis, that's my input for f, follow a line until I intersect with the f graph, and then from that point, follow a line horizontally. So if this is 200, this would be 100, and this might be, what, about 190. So I would say my estimation for my graph is around 190. So let's summarize what we did here. Okay, we found the output for the inner function. We found g of 30, and we got about 2.5. Then we used that output, right? We used 2.5 from the inner function as the input for the outer function. So f of g of 30 was f of 2.5. That was my output from g of 30. And f of 2.5 gave me about 190. Right? This means approximately equals to, when I gather information from a graph, there is an element of estimating. So that's an approximate answer. So that's graphically. Let's look at how to evaluate composition of functions numerically. So I have a table here which gives me values for x. That would be an input. I have output values for f. And then I have, this actually should just be g of x. So these are output values for g, right, with given inputs. So I want to find f of g of x for the 6 values in the table, which means I want to find f of g of 1. I want to find f of g of 2, right? Getting these from here. Right? F of g of 3. I'm going to find f of g of 4, f of g of 5, and f of g of 6. Okay. So let's do the first one. And again, when we evaluate where we have nested parentheses, we start with the innermost parentheses. So if I'm going to find f of g of 1, I want to find g of 1. Well, when 1 is my input, right, my output for g is 5. So f of g of 1 is f of 5. Now, if I want to find f of 5, then I'm going to go to where my input is 5 and my output for f is 0. So this equals 0. Let's try it for f of g of 2. So for me to find f of g of 2, I'm going to, again, start inside. I'm going to find g of 2. When 2 is my input, g's output is 3. So this gives me f of, right, my output from g, which was 3. And if I want to find g of, I'm sorry, f of 3, then I'm going to use my input for 3, right? Find my output for f, which is 6. So let's run through a few more. So let's take, that's a lovely color. All right, I want to find f of g of 3. So 3, right, gives me 2, so that is f of 2. And when 2 is my input, f's output is 4, so that gives me 4. I want to find f of g of 4. So I'm going to start with 4 as my input. I want g of 4, which is 1. So this is f of 1. 1 now is my input. I want my output for f, which is 3. This is 3. Okay. Finding f of g of 5. Let's come in here and we'll erase this so we can see what's happening. So again, this was not f. So to find f of g of 5, we're going to start with 5. Right? Find what g gives us. So this is f of 7. Now I want to find f of 7. Oh, there's no 7 in my input column. If I don't know what f of 7 is, then this is undefined. Okay. Why is it undefined? Because 7 is not in the domain of f, right? I don't have a value for x. Let's look at one more. We're going to look at f of g of 6. So we're going to start with g of 6. G of 6 is 4. So this is f of 4. And then to find f of 4, we start with 4 and we find what f gives us, which is 2. Okay, so let's look at what happens here. Okay, here I'm trying to find and compare g of f of 2 and show that it does not equal f of g of 2. Now note here that we already found f of g of 2, which was 6, so we know that's 6. So let's find g of f of 2. And to find g of f of 2, again, we're going to start on the inside and we're going to find f of 2. So input 2, output from f is 4. So this is g of 4. Now to find g of 4, right, I'm going to start with the input of 4 and pick up my output for g, which is 1. So this is 1. Okay. Does 1 equal 6? No. Okay. So what can we conclude from that? Right. What changed when we went from g of f of 2 to f of g of 2 was the order, right, that we had our functions in. When we can change the order of operations, right, a function is commutative. So what this tells us is that composition of functions is not commutative. All right, we're going to take a little bit of a look at domain and range of a composite function. So here we have a graph of G. Right, so this is our graph of G, and we have a graph for F. And I want to look at what would happen when we try to find F of G of 6. So if I want to find F of G of 6, I'm going to start with G of 6. I'm going to use my G graph. I'm going to start at 6, take a line up to my graph, and then take a horizontal line over. So if this is 4, this would be 1, 2, maybe 2.7. Right? So this is F of 2.7. For me to find F of 2.7, I'm going to go to 2.7, which might be about here. On F, take that up and then over, and I get about, I don't know, that's kind of close. I get about 2.8. Okay, so no problem in finding F of G of 6. Now let's look at finding F of G of 8. So to find F of G of 8, we're going to start with G of 8. So I'm going to go to 8 on the G graph, and I'm going to follow that line up until I intersect my graph, right? But I don't. So if I can't find G of 8, right, then I can't find F of G of 8. So this is undefined. Right? And why is it undefined? Right? Because it's undefined because 8 is not in the domain of G. Now let's find F of G of 2. So again, starting on the inside, I want to find G of 2. I go to 2 on the G axis, follow that this time down till I intersect my graph, and then over, and I get about -1. So this is F of -1. Now I want to go to -1 on the F graph, so -1 would be here, and I follow that up, right, and I never intersect my graph. So this is undefined, right, and this is undefined because G of 2, which was -1, is not in the domain of F. All right, now the rest of this is using a table of values to determine domain, and we're actually not going to cover this in these notes, so I hope that is a good thing for you instead of a disappointment. But I do want to look just at this very next topic. Okay. So our equations for G and F were these two linear functions, but each defined on a limited domain. We know how to graph that in our calculator, and if we plot each of those in our calculator, then G, right, this would be G, would be y1 equals, right, y1 equals x minus 3, given that, open parentheses, 2 is less than or equal to x, and x is less than or equal to 7. F of x we could store in y2, and that would be y2 equals -2x plus 8, right, on that limited domain. Now, if we compose those two functions, and we are looking at F of G of x, right, then we can enter as y3, y2, remember y2 is where we put, y2 is G, sorry, so this is actually G of F of x. Of y1 is F of x. So what we would see on our graph is actually the composite function, and we could pick the domain out of that. I'm going to attach a very quick video of how to do that on the calculator. Your next page of your notes, well, actually doesn't have anything in it. So let's go back here. This is what I'm looking for. This is finding domain algebraically, and we're not going to talk about that either. So that finishes our notes today. Hope that you understood what we did in finding composition of functions graphically and numerically, and the idea of composite functions.